Hello students, welcome back to JCE Connect series of lectures. In this particular lecture, I'll be taking one design example of design of slab base, and here I'll be considering both axial load as well as a moment. That is, the axial load is accompanied with moment. Then how to design the slab base. So in previous lectures and all, so we have seen simple slab base design, also the gusseted base design by taking only the axial load. But in this particular problem, I'll be considering both axial load as well as a moment. So this is the design example given, that is a design a slab base for a column ISHB 300 at 58.8 kg per meter to carry an axial load of 600 kilonewton and a moment of 10 kilonewton meter. Design also the pedestal and welded connection. Take M20 concrete and SBC of soil as 200 kilonewton per meter square. So this is the design problem given. So first what we need to do is we have to take the details of ISHB 300 from the steel table. You refer steel table and take the details of ISHB 300. Take all that is a width of the flange here. Take width of the flange, thickness of web, height, then the thickness of flange. All you take it from the steel table. Okay. Then the step number 1, as usual, you have to follow. That is first you have to calculate the bearing strength of the concrete. Then to calculate the bearing strength of the concrete, just first calculate the given load, that is make it factor, that is a factored axial load, multiply it by 1.5 into 600, so 900 kilonewton you get. Then the factored moment, then mu will be 1.5 into 10, that is 15 kilonewton meter. So the bearing strength of the concrete W is 0.45 FCK, or you can take it as a 0.6. So just I have taken in this problem 0.45 FCK, and if you are taking 0.6 FCK and calculate, that is also correct. So here I am calculating taking 0.45 FCK. 20 is the characteristic strength of concrete. Then we get the bearing strength as 9 Newton per millimeter square. Then the next step will be again you have to calculate the area of the base plate required. So again these steps will be same as previous problem design. The only change here you get is in this problem the load is, that is axial load, is accompanied by moment, and when it is accompanied by a moment, how to calculate the thickness we'll see in this problem, and rest all steps are same. To determine the area of the base plate required, then first provide a base plate of width B parallel to the flange of column. Okay, so you have to provide a base plate of width B parallel to the flange of column. So when you are providing a base plate parallel to the flange of the column, what we get? So we get that is a width of flange plus suitable projections on both the sides, and also we get like this in this problem. So this is the flange, parallel to the flange we get this width, this one. This is the flange, the parallel to this will be, we get this width. So this width is nothing but what? This width of the flange plus projections on either side, suitable projections, then we get this width. I hope you understood this one. Then that is only given here, width of the flange plus suitable projections on both sides. Here assuming 50 mm as a projection, then we get 350 mm. Then the bearing pressure, now we have to calculate actual bearing pressure, that is the combined effect of direct stress, this will be the direct stress, plus bending stress due to moment. Bending stress is due to moment. Now we have to calculate this pu by a plus m by z, where z is the section modulus of the plate. We know the section modulus, how to calculate section modulus, z equal to I by y. In previous problem also I explained about this z, how to take the z, I by y. So I is a bend, since it is a rectangular plate of thickness t, and here the thickness to be considered as a d, here thickness to be considered as a d, then BD cube by 12 divided by d by 2. Then the b to be taken here, this is to be taken a b, and the depth to be taken as a L. Okay, in this way. This one. Then BL cube by 12 divided by L by 2. Then we get BL square by 6, where length L is the length of the plate. Substitute in this formula, then we get, so we know the PU, then divided by 350 we know B, then L, then M, 15 into 10 raised to 6 Newton millimeter moment, then Z is this BL square by 6, 350 into L square by 6. I hope you understood this one. Then next, so solving the above equation, we get length as this much. Let us say length as 400 millimeter. Then provide a base plate of size L into B is equal to 400 into 350. We get this one. Then, so after getting this one, let us calculate the projections on both the, projections in the direction of length. So we know the, that is depth of the section, that is 400 minus 300. So this one. So we are calculating this length now. This one. Length is 400. 400 minus 300. We get these projections. This side as well as this side projections. So here I am getting 50 and 50. Okay. 400 minus 300 by 2. This is the projections. Then calculate what is the revised bearing stress under the steel plate. Revised bearing stress means actual bearing stress acting underneath the steel plate for the provided area of base plate. So now this is the size of the base plate provided, that is the width is 350 and length is 400. That is the area becomes L into B. Now this is the soil pressure acting, and how this soil pressure we get. So we know this formula. This is for the combined effect of direct stress as well as the bending stress. We get one value as a maximum, other one is a minimum. P by A plus or minus M by Z. So substitute the values of P as well as the M here. So when I substitute here, I'll get one value as a maximum by taking up that is a plus, one as a minimum. So these are the stresses acting underneath the column base plate. 8.04 Newton per millimeter square and 4.82 Newton per millimeter square. These two stresses. Then when I plot, so about this I explained again in the previous lectures how the stress distribution underneath the column base plate. So by taking P by A, that is P by A plus or minus M by Z, how the variation will be is all explained, and we have got the stress distribution values underneath the column base plate. Based on this one, we have got a minimum value, that is 4.82, and other one is a maximum value is 8.04 Newton per millimeter square. Then this is the upward pressure on a base slab. This is the diagram we get, and this is the plan of the base plate, and this is the pressure diagram underneath the base plate. So when this was not present and the moment was not present, the stress distribution would have been taken uniform like this. Since the moment is present here, so we get the stress distribution as a trapezium form. This is the trapezoidal stress distribution. Okay. Now we have to calculate thickness for this one. Now we have to calculate the thickness of the base slab. So again, consider this is the critical section XX at this point, and this is the base plate I have taken, and the length of the base plate I have taken as a 400 here. And let us take the critical section XX here, and the projection here is 50, and this is 300, and this is 50. This side is 50. Then 50 plus 50, 100 plus 300 is 400 is the total width. Then this column is subjected to both direct stress as well as the bending stress. Direct stress is because of the direct load acting, and the bending stress because of the moment present. Okay, so because of the combined effect of direct and bending, this was the stress distribution underneath the column base. Okay, we have calculated the minimum stress as well as the maximum stress, and also we have chosen the critical section XX. Now we have to calculate what is the actual moment at this critical section. Okay, so when you calculate actual moment at this critical section, because this is the zone of failure, we can say zone of failure at this particular section, it may fail. So what is the moment actually acting here? Then the moment of resistance of the base plate. So to calculate that one, so first I have divided this one as a rectangular, other one is a triangular. So rectangular portion, if I take from here to till here, I'll get a 4.82 till here. Then I have a maximum of 8.04 here. It will be like this. So one I get rectangular portion, then another I'll get triangular portion. Then this stress will be 4.82 throughout. This will be 4.82, and this will be 8.04 minus 4.82. You get this one as a 3.22 here, and here is a 0. I hope you understood this one. This plus this will be this one. Okay. Now at section XX, I need to calculate what is the stress here. At section XX, what is the stress here? For this one, what I have to do is, so here to here is 400. Right here, for 400 length, the stress is 3.22. So for 50 mm length, what is the stress? X 50 mm is this one. This 50 mm, what is the stress? For 400, it is a 3.22. The variation is 3.0 to 3.22. So for 50, what is the stress? So cross multiply this one. I'll get X equal to 50 into 3.22 divided by 400. So what I get? 50 divided by 400. I get 0.4. 0.4 Newton per millimeter square. Okay. I hope you understood this one. 0.4 I'll get. Now, so up to here, this one. This part, if you consider only this part, I'll consider this part. So 0.4 I am getting only this much is a 0.4, this part. Then 0.4, 8.04 minus 0.4. Then I'll get up this edge, 7.64. Because I calculated for 50 mm length, for 50 mm, this one, for 50 mm, the stress was 0.4 only. And for 400 mm, the stress is 8.04. From here to here, then 8.04, this much I get 0.4 Newton per millimeter square. Then here I get 7.64. Then if I want to calculate a moment about xx, the one part will be the rectangular, other part will be triangular. Rectangular part will be having a stress of 7.64. So it will be like this. Okay, this part is 7.64 and this will be 0.4. Okay, now the resultant will be acting here and this resultant will be here. Now you have to take the moment about xx. You will get a moment at xx. So now moment at xx will be, one I said it's rectangular portion, that is area 7.64 into 50, and the it is acting at the center, that is 50 by 2. Then one will be the triangle, that is half, base is 50 into height is 0.4, and this will be acting at a distance of 2/3 from this xx, 2/3 of 50. We'll repeat it once again. Moment at xx I am calculating. This is at xx. The stress is at xx. That is a rectangular. This is a rectangular one. 7.64 into 50, which is acting at the center, that is 50 by 2. And one more is a triangular portion. Half into 50 into height is 0.4, and which is acting at a distance of 2/3. 2 by 3 into 50. Then this is the answer I get. That is moment at xx will be 9883.33 Newton millimeter. Let us call this equation number 1. So this is the actual moment acting at xx. Acting at xx here. Now calculate what is the moment of resistance. That is the bending strength of the plate. So for calculating bending strength of the plate, we are having this formula 1.2 JE into Fy by gamma m. 1.2 is a factor of safety taken. It means 20% more the bending strength will be taken here. JE into Fy by gamma mo is actual equation, so taken 20% more. Then here JE will be Pt square by 6. We know how it comes. In previous problem also we have solved this one by considering 1 millimeter width of the base plate. So 1 into T square by 6. So we are considering this is the base plate. We have taken this is a width as a 1, then 1 into thickness. 1 into thickness 6. Then substitute here, you will get this equation. Then calculate the thickness of the base plate. Then equating equation number 1 and 2. So equate this and this. When you solve it, you will get thickness as this one, 14.74 millimeter. That is equal to 16 mm. Hence provided slab base of size L into B into T as 400. Okay, 400 by 350 by 16 mm. Here important is, this is important here. How to calculate the thickness is very important. So to calculate thickness, you need to draw first the stress distribution underneath the column. You have to considering the combined effect of direct stress as well as the moment. So this formula you have to use P by A plus M by Z. So when you will be getting two stresses, one is a maximum, other one is a minimum. So when you get a maximum and minimum stress, then you have to plot like this. Then you identify the critical section. Then you calculate moment about the critical section. So by calculating the stresses at xx. Okay, you calculate, because we know only the two end stresses here as well as here. Calculate anywhere between the sections. Okay, anywhere in between the section, that is we want at xx. So I have calculated stress at xx. To calculate stress at xx, I calculated first for 50 mm length, because we know for 400 mm length what is the stress distribution. So what could be the stress distribution for 50 mm length. So calculate for 50 mm length, then mark it, then calculate the moment about xx. So this is very, very important here. If suppose if moment is not present, so it would have been having the stress distribution diagram like this, uniform. So it is very easy to calculate uniform stress distribution. Then so once we know this pattern, we can easily calculate the thickness at xx. So finally we got this one. Then after this one, next step is what? Design of weld as usual. So let us design the fillet weld of 100% of axial load due to moment, then the load on the weld. So here we are not providing any gusset plate here, so we are taking 100% axial load, and due to moment, then the load on the weld will be 900 kilonewton. So length of the weld that can be provided is as shown in the figure. So this is the figure of the column section. You have to provide the length this side up to the root of the fillet of the weld. So you are leaving that root of the fillet of the weld up to here you have to provide, and this will be like this. Okay, so mark all the length, that is a depth, width, thickness of the web, thickness of the flange. Then from the steel table you get the root of the toe as well as this is root of the fillet. Okay, means it will be like this. So this portion, this one up to here and here, this is marked as R1, and this one marked as R2. So you have to get R1 and R2 from the steel table. You'll get from the steel table. So here it is marked. Here. So here mark is R1, root radius R1 and R2. So here you need not do any welding here, leaving that portion, root radius at the junction, this is, and as well as here. Okay, so now you have to calculate the length of the weld required. So here I marked here up to here, this one up to here is R1. So this is the thickness of flange plus R1 I have taken. Thickness of flange is 10.6 plus 11 is the R1. So this much to be deducted, this side as well as this side. Okay, similarly R2 to be deducted here. So I have marked here. So length required 2 into depth of the section minus 2 into thickness of flange plus R1, that is root radius, again plus 2 into width of the flange minus TW, thickness of web, plus 2R1 plus 2R2. Yes, both R1 and R2 here. So here I am calculating this minus this 2 times of R2, this side and this side, minus thickness of web minus 2 times of R1. This one up to here, R1. 2 D minus 2 thickness of flange plus R1 plus 2 width of flange minus TW minus plus 2R1 plus 2R2. So okay, substitute all the values. This R1 and R2 you will get from the steel table. R1 is 11 mm and R2 will be 5.5 mm. You get from the steel table. Substitute that, you will get this answer. So length required. Then once you get a length required, so you know how to calculate again. So force equal to what? Length of the weld into thickness of weld into stress in the weld. Then equate it. Force we know how much it is coming. Then length of the weld we have calculated. Then the thickness 410 divided by root 3 into 1.25. By solving we get thickness as 5.1 mm. Then the size of the weld, because S equal to T equal to 0.7 S, T equal to 0.7 S, S equal to T divided by 0.7. Okay, so I got size of the weld as 8 mm. Force equal to length of the weld into thickness of weld into stress in the weld. So this concept you have studied in welded connection as well as in previous problems I told how it comes, that is stress in that is the strength of weld per millimeter run. Okay, I hope you understood this one. Then further, the last step, depth of pedestal required. So depth of pedestal required, again as usual the procedure. So just keep the plate over the pedestal, and it is accompanied by both moment as well as direct load. So assuming the load distribution is at an angle of 45 degree both the side, take one side length of the plate 350. So before this one, so you have to take the design of concrete pedestal, take the weight coming on the pedestal, that is taking the working load on the column, that is 600, take 10% for the self weight of the pedestal 60 kilonewton, direct load we get the total load as a 660 kilonewton, then increase it by 20% due to moment. Because of the presence of moment, you would increase the load by 20%, you will get this load. Then the SB soil is 200 kilonewton given, and the size of the pedestal you get 792 by 200, you get this much. Assuming the square pedestal, then you get this one 1989 or say 2000 millimeter. So once we get that size, as I said, assuming the load dispersion will be at an angle of 45 degree, then calculate the depth required, depth of pedestal required. Assume load dispersion at an angle of 45 degree, then tan 45 is called d by 825, you will get the d as 825. Hence provide a pedestal size of this much, 2000 by 2000 by 825 mm. And at last you have to provide anchor bolts. Provide anchor bolts of 24 mm pi on all the four corners. You have to write, provide anchor bolts of 24 mm pi on all the four corners. So this ends the design. Again, the design procedure and all is same, but only thing, if it is accompanied the moment, then you have to follow this procedure. You have to calculate this formula to be used, then calculate maximum and minimum stress, then this is a pressure diagram, then you have to calculate the thickness, and rest all steps are remains same. I hope you understood this one. So please practice this kind of a problem also. So if you get the problems like this, it is accompanied with a moment, then you have to follow these steps. Okay, thank you.